Hi everyone, good evening. So we'll be starting now. So I'll quickly share my screen. Yeah, so is my screen visible to everyone?
Yes, sir.
Fine, fine. Okay. So basically, so this is analog IC design. So the course name is analog IC design, and 1 second. Okay, yeah. So the course name is analog IC design, and I am the tutor for this course. This course is taken instructed by Dr. Sankar Aniruddhan. He is from IIT Madras, Department of Electrical Engineering, and my name is Mayank Anupam. I am a PhD student, also a PMRF scholar. I am from Department of Electrical Engineering at IIT Kanpur. Fine. So before starting this week's content, which is basically negative feedback implementation, right? Circuit level implementation. Sorry, not circuit level, but block level implementation. So let me ask you. So I guess everyone was able to access the YouTube recordings, right? So last week, a lot of people had this query about my YouTube recordings. So now everyone is fine, right? Whoever wants to access the recordings, yeah, fine, fine, fine. So basically, this was already communicated on the portal, right? The links and everything, all the material also. It was already communicated to the this thing portal. I guess everyone is able to access them, so that's not a problem. Other thing that I wanted to ask you is that the solutions were also released for assignment 1 and 2, right? So does anyone have any problem with that, or any doubts with that?
We are not able to access those solutions.
Oh, that's okay. Let me check. That's absurd, actually. I don't. Okay. Okay. Let's see. Yeah, it looks like the solution. Okay, 1 second. Okay, so let me check that. Yeah, it looks like there is some issue with this. So when I click on the solution, so it simply opens the uh,
Course of basic
correct,
introduction to that
correct,
course.
correct. Yeah. Okay, so I will communicate this problem to them. Okay. So hold on. I will communicate this problem. Let's see what happens.
Also, one more point is there,
Yeah.
Mayank sir,
Yeah. Yeah.
that in the from the previous week assignment, na, it
Yeah.
was clearly mentioned that if the decimal points are not mentioned anything, na, then you can consider it as 2 points after the decimal.
Correct. Correct. Yes.
But in some of the solutions it is found that that answer is not we have I have put that as a point two this one digits after the decimal,
Uh,
but it has not been considered and it's has been given the wrong, like, so we're not able I'm not able to actually get what exactly we were supposed to do. So if we
okay.
can
So
discuss some of the questions
when
from
the
that assignment, it will be better.
yeah, yeah, so I understand your problem. So that happens actually. So I will communicate this concern to the authorities. Okay, I will mail them. You can also mail them actually. So
Yeah, yeah.
this administration part is not my jurisdiction. So it is I
Okay,
can
okay.
simply communicate your issue to them. But
Okay, thank you,
yeah,
sorry.
so I will. No, not a problem. No need to be sorry about that. It's just that I am also in the same boat if when it comes to administration. Okay,
Okay,
so I will simply communicate this problem to them, and let's see what they tell us. Fine.
okay. Thank
Yeah, yeah. Welcome. So any doubts in the previous assignment? Not first and second, or the third one. In the third assignment, do you have any problem? Anyone? So before moving forward to this week's content, I want to ensure whether,
Sir, in assignment 3,
yeah.
thou- in assignment 3, sixth problem, sir, feedback factor they asked.
Okay, let's see. So let's remove the sharing here. Stop sharing. Fine. Let's check assignment 3. Okay. So this is assignment 3, right? Yeah. So what is the problem here?
Sixth problem, sir, feedback factor.
Feedback factor. Okay. Okay. So basically, you have to find the value of k here. K. You understand what I'm saying?
Uh, yes, sir, but I don't get that. What is that in that face margin? How to find that, sir?
No, the first thing that you did you understand what I'm saying?
Yeah,
So you
yes,
have to
sir.
find the value of k here. So you understand, right? What was
Yes,
k?
sir. Yeah.
So that you have to find the value of k. So let's see. This is yeah. So you see this right? In this, the phase margin will definitely be dependent upon k, right? This k,
Yes.
not in
Yes.
this one, but if it has two poles in the system, then it will be dependent. Let me see. Yeah, so you see there are multiple poles in this particular question, right?
Yes,
So
sir.
I think we discussed a question like this where we had multiple poles in the this thing, multiple poles, correct? We discussed this question last time where we had multiple poles. So basically, the only thing that changes now is that now we have we have this feedback factor also. Where did this go? Uh, yeah. So now we also have this k minus 1 times r and this r, right? The only thing, so the question that we discussed last time, that is here, I guess, week 2. Uh, this question, yeah, this was the problem that we discussed, right, in week 2. And in this, there was only unitarian feedback. This was not a, there was no k minus r and r business here going on, right? There was no feedback ratio. The feedback ratio was 1. But when you have feedback ratio, when you have certain resistor divider here, then you the only thing that will change is the loop gain expression, right? And based on that, the phase margin expression will also change. So if you have a doubt there, okay, then I would suggest you go through this lecture once, this last week tutorial once, and then you will be able to solve it probably. If you have a doubt after that, you can ask me, okay?
Yes, sir.
Yeah. So I guess we had a very extensive discussion on this, right? So I think you should be able to tackle that problem. Fine.
Yes, sir.
Yeah, yeah. Okay. Anyway, so anything else? Any question? Any other question?
That there is noise.
Yeah, yeah. So please mute yourself, everyone. Yeah. So yeah, so is there any other doubt in any other assignment? One, two, three, anything? Don't worry. The solutions will be released shortly. Okay, and if it is not visible now, it will be in future because I will communicate this problem that it is not accessible now. I'll communicate this problem to the authorities. You can also email them. It will be sorted out for sooner then. Okay, so I guess there is no problem for anyone in 1 and 2 and 3, assignment 1, 2 and 3. So any difficulties content wise, any issues in that in the content? in the theory part, week 1, 2 and 3, because moving I will be talking about week 4 content today, so I want to make sure everyone is comfortable with 1, 2 and 3. Okay, so it looks like no one has any problem. Fine, so I'll be moving with this week's content in that case. Fine. So yeah, so this week basically we learnt about two-stage operational amplifiers, right? So in week 4 we learnt about two-stage Miller-compensated operational amplifier. So I guess I'll just quickly summarize what was taught in this week. So fine, so this is basically the amplifier here, right? Why is it called a two-stage amplifier? Anyone?
We are adding two opamps.
Correct. So this is the first one here, right? This is the first one and this is the second one, right? So that is why it is called a two-stage. Fine. And why is it called a Miller compensated op-amp?
Due to GM2 by GO1 plus 1.
Correct. So you see that the pole expression that we found out was this one, right? This was the pole expression. Correct. And for pole 1, so what is Miller compensation? It was explained in the lecture, so anyone can volunteer. What is Miller effect basically? What is Miller effect? Anyone? Okay, so I will be explaining that. So you see, this Miller theorem is actually applicable for a voltage controlled voltage source. Okay, so let's say you have this gain of minus A here in this block. This is a voltage controlled voltage source. Okay, so in the very first week we discussed about a voltage controlled voltage source. What is a voltage controlled voltage source, right? So this is a voltage controlled voltage source, and this is in its input, this is its output, right? So let's say this is input Vi, this is output Vout. So the relationship between output to input, what will it be for this particular op amp? So for this particular VCVS, it will be Vout is equal to minus A times Vi, right? This is the relationship. Now what is Miller effect is that if you add an impedance here, let's say it's called Z, the impedance is Z, okay, then if you add an impedance here in this fashion, so this is a negative feedback now, right? This is a negative feedback here. Do you understand how is this a negative feedback? Anyone? Do you understand why is this a negative feedback here?
Because when Vout increase, when loop gain increase, then Vout will be decrease.
When loop can increase, then Vout will decrease.
I am saying that
Vi is positive, V naught is negative, right?
Yeah, so I mean, okay, so fine. So this is a negative feedback, and I guess everyone understands that, but no one is able to explain that. But yeah, so this is a negative feedback because you see that this is a gain of minus A, right? This is a negative gain here in this block, and you have shorted its input and output, not shorted but connected its input and output through some path here, through some impedance Z, right? And the gain here is negative. So let's say we break the loop here and we apply a test voltage here. The return voltage that we will see here at this point, will be in a sense which will be negative of this direction, right? So let's say it is increasing, the input test voltage is increasing, so return voltage will be decreasing. Okay, will be in the negative sense of that. It will have a sense which will be negative of that. If it is positive here, then this will be negative here, return voltage. So that is why it's a negative feedback circuit. Fine. So this is negative feedback. So what Miller's theorem says that is when you have this condition like this, so the looking in impedance from this side, okay, from the input side, the looking in impedance will be Z divided by 1 plus A. Okay, that is what Miller's theorem suggests. Miller's theorem tells us. And how do you find impedance at any point? How do you find impedance at any point in an LTI circuit?
Total voltage by total current.
Correct, we do that. True. So this is Z, right? And suppose you have to find the impedance at this point here. So what will you do? Now how should I proceed? You said it is total voltage by total current. So but what voltage, what current?
Apply a test voltage.
Correct. Apply a test voltage here. V test. Okay. Correct. And now I have to find out how much current is going through it, right? So in this case, what will be the, if it is V test here, this node is also V test, right? So this node voltage here, which becomes since it is a VCVS, so this will become minus A times V test, right? Correct.
Yes,
So what is the current flowing through this? I mean in this Z, it will be V test minus A V test, right? So let's through this Z, the one of the terminal of Z is at potential Vt and other is at minus AVt, right? So it will be Vt minus AVt divided by Z. This which will be the current, right, flowing through Z. True. And this current which is flowing through Z is also flowing through this voltage source, right? Because a VCVS cannot take any current. This current here is 0. Okay, so all the current that is flowing through Z is going to come through this voltage source here, right? So this is IT, right? So what is IT is equal to Vt times 1 plus A divided by Z, and this is Vt by IT is equal to Z divided by 1 plus A. Fine. So you see that this even when you had an impedance here Z, the impedance is Z here, right? But when you connected it across in negative feedback across a VCVS of gain A, the looking in impedance from this side got decreased by the factor 1 plus A. Did you understand? So in any so this is basically what is happening here also. When this is GM2, right? This is GM2. Come to this. So this is GM2 here, correct? And you have this CC which is connected in negative feedback around it. So this diagram is not right. Let's correct it. Fine. So this is the condition that you have. So this around GM2, this is connected in negative feedback, isn't it? This capacitor CC. And so that is why the impedance of the looking in impedance of CC will be decreased by 1 plus the gain of this block, right? What is the gain of this block? GM2 divided by G02, right? Is everyone clear with that? The gain of this block is GM2 by GO2. Fine. So that is why this capacitor CC, its impedance will be decreased by this factor plus 1, right? So this is the factor by which the impedance of this CC will be decreased. So what is the impedance of CC? 1 by SCC, correct? So okay, so this is 1 by SCC is the impedance, and this will be decreased by another factor which will be GM2 by GO2 plus 1. Fine. So you can say that the impedance is decreasing here for capacitor, but you see that effectively here the capacitor is getting multiplied, right? by this factor gm2 by go2 plus 1. So that is why you see this factor here, cc into gm2 by go2 plus 1 here. Okay, so this is why it is called Miller compensation, because it is in some way using Miller's effect here. The capacitor here at this node, looking in capacitor at this node here, is basically amplified by a factor which is the gain of this second stage. That is why it is called a Miller compensated operational amplifier. Okay, fine. So note this. Okay, by the way, what is meant by compensated here? Why do we say Miller compensated? Any idea? Yeah, so any idea what why is this called Miller compensated op amp? I mean, compensate, what is the what is meant by this word compensated here?
Pole is reduced to lower frequency.
Correct. Means basically you see what is compensation? It is a way to make sure that your amplifier is working properly, and the whole. Okay, let me copy this figure. Okay. So you see, even without this capacitor, we did have an amplifier, right? We did have an amplifier even without this capacitor here. So but the problem with this amplifier was that the two poles here were what? One was basically go1 by c1, and other pole was at this node, right, which was go2 by cl. Correct? And now these two poles might be very close to each other, right? And if you have two poles which are very close to each other, what happens? Basically you will have this kind of loop gain curve. Loop gain might be like this. It will have this some DC gain, right? What will be DC gain here? It will be gm1 divided by go1 into gm2 divided by go2, correct? And then it will have this first pole p1. Okay, but then again suddenly if the two poles are very close, it will also have the second pole here itself, and it will fall at minus 40 dB per decade here. And what will happen because of this? The phase curve will look something like this. It will start at 0, okay, 0 degree, and around this it will go to minus 180 degrees. Okay, so this is not good, because in that case the phase margin will be very poor. Is that understood? The phase margin in that case will be very poor. So that is why we want to split these two poles, right? We want to make sure that this pole comes back and this pole is moved further away, so that in that case this pole P2 is moved further away out of the unity gain bandwidth. Basically, in that case your phase margin will improve. So one thing that I want to emphasize here is that I don't know whether this was understood by you or not. In any this thing, in when you were when you were learning about this Nyquist plots and all, and you learned about this phase margin thing and about that. So we want to make sure always that around your UGB, this is, let's say, UGB, and let's say this is the loop gain plot. Okay, loop gain magnitude plot. Okay, so around UGB, if you ensure that your the decay, that the rate of change, this slope at this UGB is minus 20 dB per decade, if you ensure that, then basically your amplifier will be mostly stable. Okay, so people always want to ensure that around their UGB, this is UGB, okay, around their UGB the slope of this magnitude, loop gain magnitude, is approximately equal to minus 20 dB per decade. Okay, so that is why we want to push these two poles further away, right? These two poles here, we want to make them make the separation between them large as possible. Okay, so that is why here you add a capacitor. So what does this capacitor do? it increases the effective capacitance at this node, right? So that brings this pole extremely at extremely lower frequencies. Moreover, at this node, it increases the effective conductance, right? So it pushes this pole, this second pole P2, further apart, further away from the UGB, right? So you see that in the first case, the pole P1 would have been simply G01 by C1, right? G01 divided by C1. But what this CC did, it simply increased the effective capacitance at this node, right? This factor came in because of this CC. This is the Miller factor, right? It came in, and that is why this pole P1 came down to very low frequencies. At for pole P2, you see, without this capacitor CC, it would have been GO2 here divided by CL, correct? Now with this capacitor CC here, you see this factor comes here, GM2 into CC by CC plus C1, correct? And you know that GM2 will be much larger than GO2, isn't it? Because we want the gain of this block to be high, so GM2 divided by GO2 will be much greater than 1, right? So GM2 will be much greater than GO2. So effectively you see that pole P2 has gone up. This pole P2 location has moved further away from the UGB. That is why it is called compensation, because in this way you are making sure that your amplifier is being compensated for high frequency operation. Otherwise it will become unstable due to very poor phase margin. Okay, cool. So fine. So any doubt content wise in weeks 4 content? Any other doubt? This is what I wanted to say about this. Yeah, so Abhilash. Yeah,
Sir, I have a doubt, sir.
yeah.
Explain the measurement of bandwidth using the magnitude plot.
I think this was covered last week, right? So you see that when you have this. Okay, so before that, Abhilash raised his hand. So
Yes, sir.
yeah, you can ask whatever you wanted to ask.
Sir, I am facing difficulties in the understanding the lecture, sir. So how can I approach the lectures?
Okay, so if you have difficulties, you can ask me what is the problem. So do do you have any problem with the basic understanding of? I mean,
Sir, basically I am from ANC background, currently doing MTech in communication signal processing.
okay.
I am actually first I am seeing sir like this means
Uh,
in my curriculum actually there was like different things. Sir. It is I'm facing different. So I faced some more issues.
okay, so what you can do is that you can maybe. So are you comfortable with basic
Yeah,
MOSFETs? I mean,
yes sir, yes, sir. No issues.
so MOSFETs you know, right?
Yes sir, yes sir.
Correct, MOSFETs you know. So
Yes.
I guess that is the only thing that is required to do this course. If you know MOSFET, that is enough. If you are still facing difficulties in understanding the lectures, first thing
Sir,
that you should do
even
is
though
that.
I watched all the lectures of week 4,
Hmm.
after going to solve the problems, I unable to solve the problems. Sir.
Yeah, so that's another thing. That's not.
Yes,
So first thing is that you should watch the lectures again and again. Okay,
yes,
and
sir.
after that you can maybe uh, look back to some of the references. I mean,
Sir, is it possible to solve some example problems regarding dominant pole calculation, unity gain frequency?
so that is what I am doing here, right? Last
Yes,
week
sir.
also I did something like that.
Right.
Every week I am solving some problems. So this week also I will be solving some problems, right?
Sure, sure, sir. Okay.
So if you have any other doubts, if extra questions you have, you can ask me. Fine.
Okay, sure, sure.
You can also practice some questions from some reference books, right? Like
Yes, sir.
one of the reference book I already mentioned in the previous lectures was
Yes, sir.
previous tutorial sessions was this Sergio Franco's book by basically it was Sergio Franco's book.
Yes,
The
sir.
title of this book is Design with Operational Amplifier, something like that. You can
Yes, sir.
refer to that book. You can also refer to Dr. Behzad Razavi's book on analog
Yes, sir.
CMOS.
Currently, sir, I have opted the analog CMOS mixed VLSI design course, sir, here, MTech.
Okay.
they are now currently doing teaching differential amplifiers.
Okay,
They are
so
completely.
fine. So do that and try to cope up with this. Okay, you will be able to understand it eventually. Okay, try
Sure.
to spend more time on this.
Thank you, sir.
Okay. Yeah. So now let's come back to the question of loop bandwidth sorry, UGB calculation from magnitude plot, right? So let's say this is your magnitude plot of loop gain magnitude, and this is in log scale. Okay, it is 20 log 10 of this quantity, so it is in dB. And this omega here is also, it is a log plot. Okay, so now let's say you have something of this kind. The this is the plot. Okay, let's say this is minus 20 dB per decade and this is minus 40 dB per decade. Fine. So this is the UGB, right? This is 0 dB line. So this is UGB, right? Omega U loop. Correct? Fine. So the person who asked me this question, can you unmute yourself, please?
Sir,
Yeah. So are you understanding? This is omega U loop, right?
yes, sir. Yes, sir.
Yeah. So you see, there are two poles in this particular example, right? This is P1 and this is P2. So its equation, loop gain equation, would be something like this, right? Some k divided by which is the DC can divided by 1 plus s over P1 into 1 plus s over P2. Correct? Now if now sir, if you want to calculate its UGB, then one method can be directly that you do it brute force manner, right? That you write the you replace s with j omega, right? So this will be k divided by 1 plus j omega divided by P1 into 1 plus j omega divided by P2. And then after that you find the magnitude of this L of j omega. Magnitude will be equal to what? K divided by root over 1 plus omega square divided by P1 square into 1 plus omega square divided by P2 square. Correct? This is the magnitude, and now you have to equate this magnitude to 1, right? So this is the unity gain, and the omega at which this will hold true, that omega will be omega U loop, right?
Yeah.
Correct? Uh,
Yes, sir.
yeah,
Yes.
right. So this is the brute force manner, right? But in this case, what you will see is that the equations will become very cumbersome to handle. Okay, the mathematics will become very lengthy, and it will be very difficult for you to solve it. Okay, so you can make some judicious approximations in that case. So what is the first approximation that you should make in this situation here, looking from the plot? What do you think one is the one approximation that we can make here? You see that this P1, this pole P1 is much lesser compared to omega U loop, right? The way that I have drawn it. It is very less compared to omega U loop, isn't it?
Yes, sir.
It is in log plot, okay? This is in logarithmic scale, this omega. So the way that I have shown it, this P1 is at a very low frequency compared to omega U loop. Okay? So in that case you can assume that omega U loop is much greater than P1. Okay? So if that happens, what you can say? P1 divided by omega U loop will be much less than 1, isn't it? Not Don't write it this way. Right? Omega U loop divided by P1 will be much greater than 1, right? You can say that. So if you use this approximation here, this approximation in this particular example here, so you can write it k divided by 1. You can ignore 1 compared to this omega divided by P1 square here, right? So in that case it will become omega divided by P1 square simply. And similarly for the second pole here, let's say for a very first order approximation, let's say P2 is much farther away from omega u loop, right? Let's say P2 omega u loop is much smaller compared to P2. So in that case, you can ignore this omega over P2 square compared to 1. Okay, you can do that. So you can simply write 1 here for the second term, and then you can equate it to 1. In that case, you can simply get your omega u loop directly without solving many equations. So is that understood?
Yes, sir. Yes, sir.
I mean, this is one of the way in which you calculate. You make some approximations, some judicious approximations regarding this. You assume
Sir,
that,
also,
yeah, say,
okay, sir. Also explain the bandwidth in these characteristics.
what is meant by bandwidth? So this is
Bandwidth,
the UGB,
bandwidth.
right? Unity gain bandwidth, omega u loop.
Okay, that itself is the bandwidth, right,
Yeah,
sir?
this is the unity gain bandwidth. Yes.
Okay.
Sir, unity gain frequency and unity gain bandwidth both are same.
Yeah, yeah, it's the same thing.
Okay.
Okay.
Hello, sir. I have one doubt, sir.
Yeah.
Sir, according to bandwidth is the where the gain decreases to minus 3 dB, no,
Yeah,
sir?
yeah. So that is true, but that
So
is
in
minus.
dominant pole, in dominant pole system, the P1 will be mostly that bandwidth, no, sir? Because at that P1 only, the gain decreases to minus 3
Yeah,
dB.
yeah. You see, when you simply ask bandwidth, people generally mean minus 3 dB bandwidth. Okay. In that case, you are true. You are right. In that case, the bandwidth is P1. Okay. But I have explicitly told here, right? This is the unity gain bandwidth of the loop gain. Okay.
Yeah.
Unity gain bandwidth. So unity gain bandwidth means this place where the frequency at which loop gain magnitude becomes equal to 1. Okay, so this place here. So this is the unity gain bandwidth. And this is, yeah, this is true. This is minus 3 dB bandwidth. Yes. This P1 here. But when I
Sir,
yeah, yes.
so somewhere I have seen that in order to calculate bandwidth also we can just simply multiply DC gain into the first pole.
Yeah, yeah,
So is
that
that valid?
correct. That is strictly valid for a single pole system. So that you can check when you do some calculation. You can understand that. That is strictly valid for a single pole system. Okay, not for not for systems having more than one pole.
And even this system also, even it has two pole, it is behaving like a single pole.
Yeah,
So
correct. It is behaving like a single pole. So here also you can approximately say that its bandwidth is omega u loop here. This is approximately equal to its DC gain times its P1. True. That is true. Yes.
yeah, can you just simply show me like how did we end up with that relation?
Yeah. So I can show you. Let me first solve some questions here. That is easy thing to do. You see that I have made some approximation here, right? And with this you will get omega u loop, and that omega u loop you can simply see. Oh, it can be seen directly from here, right? You see that this equation, it is k divided by root over omega u loop divided by p1 square. Omega loop square divided by p1 square is equal to 1, right? So what will omega u loop be from this equation? This is
Oh
k divided
yeah,
by omega u loop into p1. This is 1, right?
yeah,
So from this you see omega u loop is equal to k times p1. So this k was the what? This k was DC gain, right? And this
yeah.
p1 is the first
Got
pole.
it. Got
This
it.
is strictly valid for first order system.
Okay.
Okay. So now let's move forward to solving some questions for this week. Yeah, is this visible?
Yes, sir.
Yeah. So
Sir,
can
Yes, sir.
yeah,
in the previous case, so
yeah.
how do we find the Miller capacitance is there, right? So connected between output and input. So is there any formula for calculating C
Where?
CC CC capacitor CC? Is there any formula for calculating CC capacitor?
No, you are asking me the question that is asked in the assignment. Okay, so there are some constraints given on CC, right? CC has because of CC something happens to the poles location, right? Because of
Okay.
adding the capacitors, you see the pole location P1 and P2, they are dependent upon this capacitor CC, right? CC is there,
Yes, yes.
CC is here also. And you know what
Okay.
happens because of these pole locations? These pole locations determine what is the phase margin of the system, of the loop gain, right?
Oh yes.
Correct? So if you have a
Yes.
phase margin constraint given in your question, if someone says that I require certain phase margin from this system, and they are simply asking you what is the value of capacitor CC that you have to choose, then in that case you can put those numbers, and you can find a relation, right, on the capacitor
Okay.
CC using this
Okay.
pole P1 P2 and the phase margin constraints, right?
Okay. Yes.
Okay, so let's move on to the question now. Yeah, so in this question, so you see that there is some kind of feedback some feedback looking in this question also, right? Where is the feedback, by the way? Can someone identify? Where is the feedback in this system?
Drain to source.
From drain to source.
Correct. This guy here, right? Fine. Now, can someone tell me what should be the signs on A and B? I mean, which this A and B in between these two, which should be plus terminal, which should be minus terminal for negative feedback?
B should be plus, A should be minus, sir.
Yeah. How did you come with that? Or
So op amp should be placed in the negative feedback
correct.
always.
Correct. So what is the? So you said B should be plus, right? A should be minus. That is what you said.
Yes, yes.
Now, anybody else trying to would like to add something to this point? Does anyone else have any other answer? Okay, so the guy who said this A should be minus and B should be plus, your logic was that this op amp should be connected in negative feedback, right? So let me ask you another question. Uh, now tell me what should be the value of this, which should be plus and which should be minus. So let's say this is A, this is B, and which should be plus, which should be minus. Yeah, the person who said that in this question A should be minus and B should be plus, that person, please tell me what should be the answer here.
Sir, actually there is a procedure that is to be followed to analyze the circuit. Later only we can decide minus and plus terminals. Usually, see,
Okay,
for
so
most of the
could you
circuits
hold on,
we...
please? Could you hold on, please? So I have
Yes,
one
sir.
second. हेलो. हाँ भैया, रिटर्न है मेरा. हम थोड़े बिजी हैं अभी. अब भैया थोड़ी देर बाद आ सकते हैं क्या? मतलब थोड़ा हम 6 बजे तक बिजी हैं. ऐसा है तो आप कल भी आ सकते हैं प्लीज़. हम अभी थोड़ा 6 बजे तक थोड़ा बिजी हैं भैया. मेरी क्लास है एक्चुअली. ठीक है, तो आप क्या बाद में आ सकते हैं? ठीक है, कल. ओके ओके, कोई दिक्कत नहीं है. थैंक यू. Yeah, so yeah, you were saying something, right? So I'm sorry, I had some other thing. So there was a call. Fine. So you were saying something. How do you find out which terminal should be negative and which terminal should be positive? Yeah, the person who was saying something.
we should apply a test signal and we should see whether it's inverted or not.
Correct.
By following that procedure, we should
Fine.
know
So,
about the...
correct.
yeah.
So where should we apply test signal?
Actually, if you see the second circuit, the node where A is connected.
So basically this test signal application can be at any point in the loop. Okay, doesn't
Yes,
matter
yes.
where you apply. But so let's say we apply it here. We apply a test signal here. Fine. So let's say this is VT. And what do you want to check?
What appears back.
What appears back. So at this point, right, we return. So this is basically the same thing, which basically it is exactly the same procedure as a loop gain calculation. Okay, but instead of calculating loop gain, we just want to see whether the return voltage is coming as the inverted version of the input voltage or not. Okay, that's all. We just have to see whether the return voltage is coming in the same sign or is coming with the negative sign of the input voltage. Okay, so this is your test voltage here. When you apply a test voltage here, what do you think should come here? I mean, let's say it is plus, it is minus. Okay, so what will happen? This will be in the same sign, right? This will be Vt times some constant. Okay, and this will be in the same sign. If this is plus, this will also be plus, right? Because we have applied Vt to the this A terminal, and A terminal is plus, so this will also be plus at this point. Correct? Fine. Now if this is plus, then what should happen here? This is a MOSFET, right? A MOSFET from gate to drain, what is the phase shift? I mean, what is the
180 degrees.
correct? I mean, there is an inversion, right? From gate to drain, if you apply a voltage at the gate, then in the drain it is inverted, right? It is inverted at the drain terminal, isn't it? You remember that
Yes, yes,
in
sir.
in normal amplifier, normal this is common source amplifier. If this is the input here, Vt, this here is what, Gm times R. Let's say it is Rd. So this is minus Gm times Rd times Vi, right? There's a minus sign here.
Yes, yes.
So this is inverted, isn't it? So this here will be if this is plus here, then this will be minus here, right? So you see that the sign that we chose first was right. But this is indeed plus and this is indeed minus, because when we apply a test voltage in this fashion, in this configuration of plus and minus, the return voltage is negative of what was applied, isn't it? So here A is plus and B is minus, correct? But in this case A is minus and B is plus, isn't it? So here also you can see if A is minus and B is plus, then you can see if you break the loop anywhere, let's say at this point, if we break the loop at this point, let me use another color here. If we break the loop at this point, and let's say we apply a test voltage at here, right? So if this is plus, the test voltage, since it is connected to negative, it will be negative here, right? The output here will be negative. And you see this is a common gate structure, right? This MOSFET here, you apply something at its the input is at its source and the output is at its drain, right? So this is a common gate structure. I guess you know these things.
Yes, sir.
If
Yes,
you
sir.
do
Yes,
not
sir.
know, don't worry. I mean, it will be taught later, but I just assume that everyone knows these things. I mean, these are basics, so that is why. So yeah, so this is if this is a common gate structure. So if this is negative here, this will also be negative here, right? So that is why now you see the input was plus applied at this node here, at the 8th node, and the return voltage is negative. So the return is inverted version of what was applied at the input. So that is why for correct negative feedback, what do you have to do? A is negative and B is positive. Cool. So this I just wanted to just put there.
So please explain this again.
Okay. So how do you find out whether a system is in negative feedback or not?
By checking loop gain.
Yeah. So this feedback here, this feedback which is highlighted in yellow here, okay, this is a feedback
Yes.
circuit. Now this feedback can be either positive or negative. You do not know that, right? So
Yes, sir.
but we were given the option that you can make this feedback either positive or negative by choosing the signs of A and B, right? What should be plus terminal, what should be minus terminal, that is in your control. And the constraint that is given to you, that is placed on you, is that you have to ensure that the whole system is in negative feedback. Okay, now for negative feedback to happen, what do you want to ensure? What is negative feedback at its very core? It is basically that negative feedback is the name comes from the fact that when you apply a disturbance in the system, in the loop, okay, at any point in the system, in the loop, when you apply a disturbance, the loop will try to correct that disturbance, right? It will
Yes,
try
sir.
to come back to the same point, right? Let's say this is a classical example, right? This is a bowl, right? And let's say if you put it is placed on a surface, okay, and if you put any ball at this point here, it will try and slide down to this point, right? Correct. And if it is placed here also, it will try to slide back to this point, correct? Now from this is a stable point, isn't it? This point here is its stable point. If you perturb it slightly from this point in this direction or this direction, it will come back again to this point, isn't it?
Yes, sir.
So this is what is negative feedback here also. What is what is compelling, I mean, what is ensuring this negative feedback here? The gravity is ensuring that, right? Gravity and the shape of this ball is ensuring that negative feedback, correct?
Yes,
This
sir.
negative feedback is ensured by gravity and the shape of this ball, okay? This ball this ball is actually making sure, negative feedback is making sure that the system, the whole, this ball and this whole system stays in the same manner that it is supposed to, that it is staying right now, right? This whole system
Yes.
is making sure if you disturb slightly from this point or this point, it doesn't matter, it will come back to the same point. So that is negative feedback, okay? So any disturbance, so that is why when you disturb it slightly from to move it to this direction, okay, to this point, this was a disturbance, right? When you moved it slightly in this direction, it was a disturbance. So what did the system do? System made sure that this ball comes back to the same point, right? So
Yes.
any disturbance that you apply, the system will try to correct it by sending a signal which is inverted version of the disturbance, right? So you are disturbing it by making a force in this direction, right? But the system is applying a force in this direction. So you see that your input was in this direction, but the return is in this direction. It is an inverted version of itself, isn't it?
Yes, sir.
The sign is inverted, correct? So now here also you just have to ensure that the disturbance that you place in the system, in the loop, that is being corrected by a signal, a return signal, which is negative or inverted version of the disturbance. So let's say, and how will you check that? You will check that by breaking the loop somewhere, isn't it? So I will break the loop at this point because I like this point, okay? You can break the loop at any point you want, but I like this point, so I will break it here, okay? Now I break the loop here and I apply an input here, I disturbance here. Let's say this disturbance is increasing, okay? I apply a voltage at this point, which is an increasing voltage, okay? Okay.
Yes.
So if
Yes,
the
sir.
voltage at this point is increasing, let's say this is minus. I select randomly. I will check if this selection is not correct. Let's say this is this terminal A is minus and terminal B is plus. Okay, I choose this as a random choice. Let's say if the system, if because of this choice, if the system turns out to be positive feedback, then I will simply swap this, right? I'll simply change this.
Yes,
This
sir.
is one of my choice. So this, let's say this is A is negative and B is positive. In that case, and I apply an input which is increasing, okay, at the A terminal, okay. If the input at A terminal is increasing because of the negative sign of A, what will happen to the output of this GM?
Output GM will be negative.
Correct. It will decrease,
Uh,
isn't it? Right, right.
yes, sir.
You are right. It will be inverted. I mean, if A is increasing here, this output will be decreasing. Correct.
Yes, sir.
Now, if this output is decreasing here, this terminal here, this is decreasing, right?
Yes, sir.
So, if this is decreasing,
Excuse me, sir.
yeah,
Sir, applying input at the A increasing, is it greater than 3 volt or less than 3 volts, sir?
doesn't matter. If it is anything, if it is increasing, what will happen to the output?
Sir, if it is less than 3 volt, means it is 3 volt dominant, right, sir?
Right, right. So, if
And then,
I am saying that it is decreasing, it is increasing. So, that is what I'll come back to that. Okay. So, let me
sure,
first finish this.
sure, sir.
Yeah, yeah.
And sir, we are supposed to ground the input voltage, right?
Yeah, yeah, that is true. That it doesn't matter, by the way. If you assume it is, so that is what is grounding mean. You just assume some reference, right? When you grounded it. So if the reference is grounding means what? Reference is 0 volt, right? You can assume
Yeah.
any reference here. 3 volt,
Yeah.
100 volt, 1000 volt, doesn't matter. It's just that you assume some reference which is 0 volt. to make your life comfortable. It doesn't matter with the selection of that reference. Okay.
That and the Vin also we need to ground
Yeah,
it, right?
yes, true. That is, by the
VL.
way, correct. Vin we have to ground. This input we have to ground. So, but that I am not considering right now. But yeah, that is correct. So for loop gain calculation, you have to ground Vin. But I'm just checking what is happening right in the circuit. But yeah, that is true. If you have to ground Vin. So this is, by the way, desensitized. Okay, this is desensitized. But anyway, I was at this point. So yeah, so when A is increasing here, the resulting voltage here is decreasing, right?
Yes, sir.
And when this voltage is decreasing, so
Then voltage will increase.
which voltage will increase?
Mm. Then voltage, sir.
Why should it increase?
Decrease only, sir.
No, it is a common gate architecture. Okay, from source to drain, the signal is not inverted. Okay, it is in the same phase. Okay.
Yes, sir.
Okay,
Yes.
so when this is decreasing here, the signal here will also decrease. Okay, it will also decrease.
Yes, sir.
So that is why now you see, this is the return voltage, right? This is the return point. This point is the return point, and you see that because of an increasing voltage at A, the return was decreasing, isn't it?
Yes, sir.
So you see that it is a negative feedback, isn't it?
Yes, sir.
Correct. So now you understand.
Yes, sir.
Correct. Fine. So there was some question regarding 3 volt. Okay, so the guy was asking whether it should be 3 volt or what. So this 3 volt is just arbitrary. Okay, you have to assume some reference here. Okay, you have to assume some reference here, and for loop gain calculation, that some reference is simply 0 volt here. You can assume any reference, it doesn't matter. Okay,
Yes, sir.
some guy was asking whether it should be 3 volt or 0, it should be grounded. Doesn't matter, as long as you make sure that this is constant while you are calculating this loop gain thing. Okay,
Okay, sir.
fine. So moving forward, so in this question I just wanted to make sure that this concept is delivered about negative feedback. How do you find out what is the sign of respective blocks? Cool. Moving forward, let's come to this question. So is this visible?
Yes, sir.
Yeah. So figure 1 shows a negative feedback loop with a 2-stage op amp without a compensation capacitor. Right. Now consider the parasitic resistance of output stage to be absorbed within R. So this GM, right, this is the output stage. This is GM. It will have some output resistance, right? It will have some output resistance. But let's say that output resistance is being absorbed by this resistor R. Okay. This will be there, but it will be absorbed. It can be absorbed here, right? So that is what is meant by this question. Let's say this is consider this parasitic resistance of output stage to be absorbed within R. So I want to design the op amp to satisfy the condition of critical damping. Okay. So now how do you proceed? First of all, do you identify what kind of this architecture is this? This is a 2-stage op amp, right? It is a 2-stage op amp. There are two gain stages in this, isn't it? So it's a 2-stage op amp. Now another thing to notice here is that this capacitor CC is not there, right? This is not a Miller compensated op amp. It is a simple op amp. There is no Miller compensation here, right? So it is a simple op amp. Now so now I want to design it for critical damping. Okay, so what to do? What is critical damping, by the way?
Zeta equal to 1.
Correct. Zeta is equal to 1. Let's write that. Correct. So what is meant by zeta, by the way? From where does this come? So this is the equation, right? The famous equation of any second order system. Second order system, it will have some numerator, right? But the denominator will be of what kind? of
S
any second
square
order
plus
system.
2 zeta omega ns plus omega n square.
Right, so it will be s square plus 2 zeta
2.
omega ns plus omega n square. Correct. True. Now this is the characteristic equation, right? The denominator d of s is equal to what? S square plus 2 zeta omega ns plus omega n square. What is this? This is also called as not this, but when d of s is equal to 0, this will be simply meaning what? S
Poles.
square plus 2 zeta omega ns plus omega n square is equal to 0. Now this equation here, it is also called as what?
Quadratic equation.
Characteristic equation.
Characteristic equation. Fine. Fine. So the speciality of this characteristic equation is that everything that you want to know about the system, the behavior of its, the transient behavior of the system, okay, that will be that is there basically in this characteristic equation. I mean, whether the system is stable or not, or whatever, you can know from this characteristic equation. Okay, that is why the name characteristic equation. Okay, so in this characteristic equation, if zeta, this zeta factor, it comes out to be equal to 1, then you can say that it is a case of critical damping, isn't it? Fine. So how do you find out? How do you do that here? First of all, why is the question of critical damping? I mean, let's try to analyze it one by bit by bit. Okay. So the question is asking that I have to satisfy the condition of critical damping, right? So who said that the critical damping has to occur? I mean, for the critical damping to occur, the system should be first of all second order, isn't it? There should be s square plus 2 zeta omega n s plus omega n square, right? The system should be second order. Now, who said that it has to be? It will be second order here. I mean, what is the system second order or not? By the way, the system.
It's a
Yes.
second order only.
Yeah. How do you know that it is a second order system?
We have sir two C1 C2 capacitors
Correct.
and storage elements.
Yeah. I mean, they basically the two
Because it
capacitors
has
here.
two poles.
Yeah, there are two poles in the system. Correct. These two capacitors here, they are separated. They are separate capacitors, isn't it? And on both these capacitors, initial conditions can be fixed independently. Okay, so that is why these two capacitors are independent of each other, and they are setting independent poles, right? That is why you have two poles here. Correct. In this system, there are two poles in the system. So when you close a negative feedback around the system, by the way, this is the negative feedback, isn't it?
Yes,
This
sir.
whole system is negative feedback. So when you close this second order system in a negative feedback, the resultant system will again be negative feedback system with second order characteristic. Okay, so that is why it is a second order system, and that is why the question was asked that you have to ensure critical damping in the system. Okay. Okay.
Yes, sir.
Okay. Fine. So now what to do? How to ensure critical damping? So definitely you have to write some equations, right? So let's proceed. So first what I will do is I will simply write the equation of the whole system, okay? The closed loop system. So what will be the closed loop system equation here? V naught by Vi. What will it be? I mean, how to find out V naught by Vi?
Voltage division rule at V naught, sir. Here V minus is equal to V naught by 2.
Yeah, correct. So we'll have to solve that equation, right? A lot of KCL KVLs. Correct?
Yes, sir.
Correct. So, but there is a easy way also here. So you see that if
Sir,
you
I
have
have
a
a
system,
question.
yeah. What is the
Sir,
question?
here in the figure, second stage is a it is a open loop, right, sir? There is no feedback for that. It is directly open loop system, right?
Yeah, I said now there is no capacitor here. There is no
Yes,
capacitor
sir.
here. It is
So
not
it
open
can
loop.
work as a comparator, right, sir?
No. Whole system is a negative feedback, isn't it? The whole system is a negative feedback.
Let
Correct.
I agree, sir. First, OPM is in negative feedback system. What about second, sir?
No. There is no negative feedback individually for the first or second op amp. The whole two-stage amplifier is in negative feedback, isn't it?
Okay.
I mean, how do you why do you say that it will work like a latch or comparator? For that to happen, the whole system should be open loop, right?
Yes, sir.
But here there is a closed loop. It is a closed loop, right? There is a
Yes,
this thing. There is a loop around it. The
yes,
system
sir.
is in negative feedback, and there is a loop,
Yes.
correct? Fine. So I was saying, how do you find out the this value? So if you have this Vi, then there is plus, then there is minus. Okay, and let's say this is whatever A of S. Okay. K minus 1 times R. This is R. Okay. This is V naught. Okay. So what is the equation? Let's solve this. Okay. What is V naught is equal to Vi minus V naught by K, right, into A of S, correct? This is for this system. So from here what you will get? V naught into 1 plus A of S divided by K is equal to Vi into A of S, correct? From here you will get what? V naught by Vi is equal to A of S divided by 1 plus A of S by K, correct? So now let's simplify it slightly. Let's make K common here. That will become A of S divided by K plus A of S, correct? Now bring A of S to a denominator, K into 1 over 1 plus K over A of S. Okay, make it even simpler like this, 1 plus 1 over A of S divided by K. Now what is A of S divided by K here? But first of all, what is K here? So this is, by the way, V naught by Vi. Okay, and what is K here?
Gain.
K is
DC
the
gain.
DC gain, right? K is the DC gain from
Yes.
input to output, right? So at DC, S is equal to 0. I mean, right?
Yes.
K is supposed to be the DC gain, right? If the gain here, A of S, A of 0 were infinite, in that case, the DC gain from here, if A of F0, what is at DC? V of V0 by Vi at 0, at S is equal to 0, is simply K divided by 1 plus 1 over A of 0 by K, right?
Yes,
Correct?
sir.
Now if A of 0 is infinity, then this will simply tend to K, right? So this is basically supposed to be the ideal DC gain, right? K is the ideal DC gain from input to output. Okay, and what is A of S by K? This term A of S by K. This is the loop gain. Okay, this is the loop gain here. What is the loop gain here? How do you find out? You break the loop here. You apply some test voltage. What is the test voltage? Vt. Then this will be A of S times Vt. Okay, and this will be what? Divided by K, right? This will be A of S times Vt by K, and then you divide by Vt. So this will be A of S by K, the loop gain, right? Is that clear?
Yes, sure.
Correct. So your loop gain was what? A of S by K. So this one here, this term here, V naught by Vi can also be written like this, right? This is equal to ideal DC gain divided by 1 plus 1 over loop gain, isn't it? Is that clear?
Yes, sir.
Correct. So this is what we will use in this example here. Otherwise this will become very I mean, this is directly we can simply find out what is the loop gain, and then we can simply use this v0 by vi divided is equal to ideal DC gain by 1 plus 1 over loop gain. This will make our life comfortable. Okay, fine. So let's find out what is the loop gain here. So how do we find out what is the loop gain here? What do we do? So please guys help me. This was covered in week 1. What is the loop gain here?
Break the loop, apply the test voltage, and measure the return
So
voltage.
correct. So where do we break the loop here? Where should I break the loop here?
Just after the feedback.
Let's say here, right? Let's say I break the loop here. Here, okay. And after that, what will I do? I'll apply a test voltage. Okay. After breaking the loop here, I apply a test voltage here, Vt. Okay. When I apply test voltage here, and I have to find what is the V return voltage here, isn't it? So what is the expression for V return? Yeah, tell me.
V0 by K.
Yeah, what is I mean, what is everything? I mean, tell me in terms of Vt. V returns in V return in terms of Vt. So it is minus Gm times. So let's ignore minus sign. That is basically minus comes because of the fact that there is negative feedback around it. Okay, so let's remove minus. So it is Gm divided by R naught. It is Gm R naught divided by 1 plus SC1 R naught into Gm. Again this part Gm R, not this is G 2 times Gm R divided by 1 plus 2 SC2R into 1 over 2. Okay, so you do it and you see that this is the equation. Okay, this is very easy to see, by the way. Okay, directly write it. So this is the V return and into Vt. Okay, so what is loop gain? L of S, it is equal to V return by V test. Correct. So that is equal to Gm times R naught divided by 1 plus SC1 R naught into 2 times Gm R divided by 1 plus 2 SC2 R into 1 over 2. Okay, so this is your, yeah. So Nilima, please, what is your doubt?
Yeah, so why it is that 2 times Gm is taken here in this expression?
Yeah, it is actually when you calculate loop gain, this 2 comes. Okay.
Okay.
Oh, this is, by the way, DC gain. What is it? I have simply written it like this. So Gm times R naught, you understand, right? Here, the first one.
Yeah. First one is okay.
This
Second
is the DC
time,
gain, right? Gm times R naught is the DC gain, right? For the first stage. So for the second stage, what is the DC gain for the second stage? It is Gm and multiplied by whatever output, whatever the resistance comes at the output, right?
Yes.
So what is the resistance at the output? It is R and R in series. This is 2R.
Yes.
Correct?
2R. Okay.
So this is 2 times GMR. Correct?
Okay. Thank
and this 1 by 2 comes here at the last because there is a from here to here we have a resistor divider, right?
Divided. Yes.
Correct. So that is why 2 comes here.
Thank you.
Fine. Okay. So this is the loop gain. So let's copy it and paste it somewhere. Okay. Okay, so this is the loop gain. Okay, so what did we say? What is V naught by Vi? It is equal to ideal DC gain divided by 1 plus 1 over loop gain. Okay, and what is ideal DC gain here? What should be the ideal DC gain? I mean, if everything is working properly, the loop gain is infinity, what is the ideal thing that is this loop is supposed to maintain? What is the relation that this network is supposed to maintain between V0 and Vi if everything is working properly.
V naught equals to V in by 2.
No. V0
V
is
naught
equal
is 2 bi.
V0 is equal to 2 times Vi. Okay. So in ideal case, this
Ah, yes, sir.
V0
Yes, sir.
by 2 is compared, right? This is V0 and this V0 by 2 is being compared to Vi, right? This is Vi and this is V0 by 2. So at when everything is working fine, this op amp will have infinite gain. In that case, this Vi will be made equal to V0 by 2, right?
Yes, sir.
Yeah, right. So ideal DC gain is, let's write it here. Ideal DC gain is equal to 2, right? Correct. So now we have everything that we need here to write the loop gain here. No, to write the closed loop gain here. So V0 by Vi is equal to what? 2 divided by 1 plus 1 over this guy here, right? Which is what? Oh, let's before that let's simplify it. Okay, so it will be V0 divided by Vi is equal to, so ideal DC gain, let's denote it in terms of K divided by 1 plus 1 over L. Okay, so I guess everyone is comfortable with this notation. So K is ideal DC gain, L stands for loop gain. Okay, so it can be simplified like this, right? It will be K times L divided by 1 plus L. Correct. So this is 2 times GM times R naught divided by 1 plus S C1 R naught. This is the first term. Put a bracket inside here, into 2 times GM R divided by 1 plus 2 S C2 R, okay, into 1 over 2. Fine. This is the first, this is the numerator. Now the denominator is 1 plus L, right? 1 plus L. So what is L? It is again GM times R naught divided by 1 plus SC R naught into 2 times GM R divided by 1 plus 2 SC2 R, okay, into 1 over 2, into 1 by 2. Correct. So this is the V0 by Vi expression. This 2 and 2 cancel, okay, this 2 and 2 cancel here. So what is it? V0 by Vi is equal to what? It will be 2 times GM times R naught divided by 1 plus SC1 R naught into what? GM times R divided by 1 plus 2 SC2 R, okay, divided by, now let's solve the denominator. Let's solve the denominator by separately. Okay, so this is the denominator, right? And remember that we are only interested in the denominator, right? We do not, for just, if you just want to make sure that our device is critically damped, okay, then we are just interested in the denominator, right? We do not know what is numerator, we do not care what is numerator. Okay, we just want to make sure that some relation holds between the coefficients of the denominator, right? So now let's only consider the denominator here. Let's remove this, no need to simplify it, only consider denominator here. Okay, so the denominator is what? It is 1 plus GM times R naught, where 1 plus SC1 R naught into GM times R divided by 1 plus 2 SC2 R. Correct. So what will it be? We take this the LCM, right? This will be 1 plus SC1 R naught into 1 plus 2 SC2 R in plus GM times GM square R naught into R, right? Divided by everything else. 1 plus SC1 R naught into 1 plus 2 SC2 R. and this denominator, this is this we have to equate to 0, right?
Yes, sir.
Correct. So this becomes our characteristic equation, isn't it? So this becomes characteristic equation. Okay. So yeah, so what is the now let's write it in terms of that, what, s square plus 2 zeta omega ns plus omega n square. Let's write it in this manner. So what is the coefficient of s square here in this, in the numerator here? So let's remove this, right? It doesn't matter, because this will simply, so this part here, the denominator part here, this will simply multiply with 0 and become 0, right? No need to consider this. So I'll just erase this here, and sorry, so let's write it, expand it. So it will become s square times what?
2 C1 C2
2
R
C1
naught.
C2.
Correct.
Yes, sir.
Cool. Plus what is the coefficient of s?
2 C2R plus C1 R naught.
Correct.
Yes, sir.
Plus gm square r naught r, right? This has to be equal to 0, correct? So from here, let's write it in this fashion here. So s square plus c1 r naught plus 2c2 r into s divided by 2c1 r naught c2 r. This is the second term, and the third term will be gm square into r naught into r divided by 2c1 r naught c2 r is equal to 0, right? So what is omega n square from this?
Sir, there will be constant plus 1 will come, right, sir?
No, what should
Plus
be,
1.
why should there be plus 1?
Multiplication, sir, 1 into
Which
1, 1.
plus will come?
Where is this plus 1?
Sir, here only numerator. We got a square
Oh,
coefficient,
sorry,
s
sorry, sorry,
coefficient.
sorry.
1 will be there, 1
Yeah,
plus.
sorry,
Yes.
my bad. Correct. Right. I'm sorry. Yeah. So this is plus 1. Yeah, so this is the right, this is the thing, right? Now what
Yes.
is omega n square?
This whole thing, sir. GM square R naught R
Correct,
plus
the
1
third
divided
term.
by.
Gm
Yes.
square r naught r plus 1 divided by 2c1 r naught, sorry, c2 r. This is omega n square. So from it, omega n is equal to under root
Under root.
gm r naught r plus 1 divided by 2c1 r naught c2 r. Okay. And what is zeta?
1.
No. Zeta is 1, right? But what is zeta here?
We should compare, sir. 2 zeta
Correct.
omega n equal to this
2
whole thing.
zeta omega n
Omega
is
n.
equal to
Z R naught.
c1 r naught plus
Yes,
2 c2
2
r
C2 R.
divided by 2 c1 r naught c2 r. Correct.
Yes,
So from here zeta will be equal to 1 by 2 times this guy here. Okay, have I done some mistake somewhere? No, not a mistake anywhere. Fine. 2 c1 r naught c2 r into under root 2 c1 r naught c2 r divided by gm r naught r plus 1. Correct?
yes, sir.
Yeah. And this we have to equate to 1. Correct?
Yes.
Now there are some things given in the question. So what are the things that you are given in the question? That r naught is equal to 100 times r. Okay? And gm r naught is equal to 1k. So let's put this here. R naught is equal to 100 times r. Okay? And gm times r naught is equal to what? 1k.
1.
Which is equal to what? 10 to the power 3.
Yes.
These two information are important. So now let's start removing. Let's start solving this. So zeta here is equal to what? It has to be equal to 1, and this is equal to 1 by 2 times C1 times R naught. So let's replace R naught by 100 times R. Okay. So it will be 10 to the power 2 times R. Okay. Plus 2C2 times R divided by 2C1, and again R naught is replaced by 100 times R. So it becomes 10 to the power 2 times R square times C2. Correct?
Yes, sir.
And then this is here again 2 into C1 times 10 to the power 2 times C2 times R square. Correct? Divided by GM R naught is what?
10 to the power 3.
10 to the power 3. Correct?
Yes.
And let's assume that this GM R naught R is much greater than 1. Okay.
Greater than 1. Yeah.
Remove this 1 from our face. So this one is creating problems, right?
Yes.
The GM R naught is 10 to the power 3, and oh, there is some mistake somewhere here.
I think that is GM square, sir.
Right, this is GM square, correct. That is why the dimensions were not matching here. It is GM square here. This is GM square here. Yeah, it is GM square here. I forgot a square term here. Fine, thank you for making it right. This is GM square. So GM times R naught is 100, 1000, and other GM times R is what? GM times R naught is equal to 1k. So what is GM times R? Is equal to 10, okay? Because R is equal to 100, R naught by 100, right?
Yes, sir.
Yeah. So it's simple maths. Okay, so this is another 10, okay? And then we will have this R square term here, okay? We will have, right, R square term also. We will not have R square term. We will only have, 1 second, okay?
R only.
Only
Yeah.
R, right? Not R square. Correct. No, we'll not have anything. We'll not have anything here actually. Right?
So in the numerator also we'll have R.
Really? No. We'll have R square. It is correct. Numerator is correct. C1 times C2, and R naught is what? 10 to the power 2 times R. So
Yeah,
this will
got it,
become
sir.
R square, right?
Yeah.
Right now?
Yes, sir.
So numerator is correct, denominator is also correct now. Now let's simply solve it. So what will it be? So zeta is equal to 1 is equal to 1 by 2. So let's push this 2 to this side. This is 2 and this is what? Make R common from here, and 1 R, sorry. Yeah, so this R and 1 R cancel from here, okay? So, okay, so from this it becomes 10 to the power 2 times C1 plus 2 times C2 divided by, this is what? This is 2 times C1 into 100, 2 times C1 into 100 R into C2 multiplied by 2 times C1 C2 into 100 R square divided by 10 to the power 4. So what will it be? 2 is equal to, and this 10 square C1 plus 2 C2 divided by, this will be what?
272
This
R.
R and this will cancel, right? And we'll have only under root 2 C1 C2 times 100 into 1 over 10 to the power 2, correct?
Yes, sir.
Right? Now again let's approximate. What should be the next approximation? What do you think? And from this also you can solve, but let's make our life even easier. So what should be the next approximation here? Assume C1 is much greater than C2, okay? We assume that C1 is much greater than C2.
Yeah.
Fine?
Yes, sir.
Then 2 is equal to, so this term will simply go away, right?
Yeah.
So it will be 10 to the power 2 times c1 divided by root over 2 c1 c2, and what is root 100? Root 100 is simply 10, right? 10 into 1 over 10 square, correct? And this 10 square go away, so you simply have what, uh, 20 is equal to what, c1 root over c1 by c2 into 1 over 2, correct? So c1 by c2 under root is equal to what, uh, 400 times 2, correct? So this was the question, by the way. Oh, I didn't say what was the question. So we have to find the relationship between c1 and c2 to make sure that the damping is critical. Okay, so you say that c1 by c2 is what, it is 400 into 2, which is c1 is
800.
actually, c1 by c2 is actually equal to 800. Okay, so what does this mean? C1 is equal to 800 times C2. So I think this justifies our assumption, right? We assume that C1 is much greater than C2, and this turns out to be the right assumption, because C1 from our calculation it came out to be 800 times C2, which is much larger than C2, right? So our assumption was correct. Even without assuming this, you could have solved this question, right? By assuming that c1 by c2 under root is equal to x, so you would have gotten a quadratic equation, and then you could have solved it. But even without that, we can make this approximation and simply solve it directly. Okay, so this was the question. Now the second part is, what must this relationship be for unity gain configuration? So in unity gain configuration, you just assume that there is this feedback is not, this r v0 by 2 is not there. Okay, it will be simply v0 again here. Okay, and you just have to assume that the resistor r is here like this, and this is directly shorted here for the second part, and this will be solved similarly in the same manner that we solved this question. Okay, so any doubt here? Did you understand what we did?
Yes, sir.
Yeah, someone was asking something.
Sir, how to find R out here, sir?
Which r out?
R out of the total amplifier.
Yeah, there was a question. Okay, so thank you for reminding me. There was a question here in the assignment. So in the assignment there was a question that so let's see the third problem. This
In
is,
the second part, sir,
yeah,
in the second part, we will simply remove R now.
which second part?
Instead of R, we will short circuit that R.
Yeah, you have to remove this R, and you simply have to short circuit here and this R.
Yes.
But by the way, you have to keep some resistance, right, at the output here. So that resistance R you put here. Okay, that's all. No, don't worry about that question. Okay, the point is, did you understand this part or not? What we did and why did we do that? I mean, the question, how did we
Yes,
proceed? That is the most important thing. So
yes, understand.
correct. Now let's move on to the that question about output resistance thing. You see, this figure looks like exactly the same one that is there in your assignment. Okay, so you see, what happens is that how do you find output resistance in any case? How do you find resistance? Looking in resistance at for any network that you are given. Let's say this is a network here. Okay, this is a network here, some LTI network, linear time invariant network. How do you find the looking in impedance here?
We will deactivate all the independent sources, sir,
Correct.
and apply a test voltage or current source.
Correct. So we
Calculate
deactivate
ratio
all
of
the independent voltage sources or current sources here, and then we apply a voltage source here, right? And find out what is the current. Correct? Right? Fine. Now, exactly the same thing you have to do anywhere that you are asked this question. Okay. So in one of the assignment, in your next assignment that I have seen, is that you are asked to find out what is the output impedance here. Okay, in this network. So how do you do that? What will you do?
We will short the input.
We'll short the input. You have
Due
installed
to
that what?
due to Mitchell ground concept, the node voltage will force it to zero.
What? What will you do?
So due to Mitchell ground concept, the that where we are interested to find that voltage also force it to 0 volts.
No, no, that is when the amplifier's gain is infinity. That is not the case here. Okay.
Okay, sir.
Yeah, yeah. So first thing you have to desensitize the input. That is true. You have to make it ground here. Then what you have to do? You have to apply the test voltage here. Okay.
Yes, sir.
And find out, this is Vt, and find out how much current it is taking is going out of this. So that will be your output impedance. Okay. Vt by It is your R out. Okay. So that is how you have to do it. Okay.
Yes, sir.
Yeah. So in the question, be mindful what they are asking. Whether they are asking only the output impedance of this part, or they are asking the output impedance of everything. If they are asking everything, that means you also consider this one, these two guys here. If they are asking only the output impedance of this op amp, then you have to ignore these two guys here. I mean, while calculating output impedance, you remove these two from the from calculation. Okay. So that is how you calculate output impedance. Fine.
But sir, here he is asking overall. Overall means I didn't understood what they want to tell you. Like overall means including the feedback or just like open only. He is asking. I didn't understood this thing.
Let's see what they are asking. What is assignment number 4? Okay. Determine the overall. What is overall? Yeah, so they are only asking this one without the capacitor and the resistor. Okay, that is what they mean. They are only asking this part,
Okay, sir.
only this part. Okay, without these two guys. Okay, that is what they are asking. Fine. So yeah, so I don't think we have enough time. So let's quickly do some simple questions here. Yeah. So first of all, in this case, in this figure, which terminal should be connected to the output to make sure that the whole loop is in negative feedback? I mean, whether I should connect this or whether I should connect this. Which should I connect? What should I do?
Above.
Below.
Below one.
Below one. Correct. Oh, there was a plus and minus sign given here. Okay, okay. Cool. But you understand, right? How do we do that? This
Yes,
is
sir.
correct. Fine. After that, mm, let us do what is the first pole location? P1 in this case. This is a Miller compensation, right? So in Miller compensation, you can approximately say P1 is equal to what? What is the location of P1?
Is it 4 times P2?
No. That is for a particular case. That is for critical
Okay.
damping. Okay.
Okay. Okay.
Uh, I'm not asking that condition. I'm asking for what is P1? The expression of P1 in terms of GM1, GM2, the C, this G naught here. Okay. In those terms, what is the value of?
Then GO1 upon C into GM2
Correct.
upon
So it is
GO2 plus
GO1
1.
divided by C into GM2 divided by G02 plus 1 approximately, right?
Yeah.
There is no capacitor here, so we do not have to worry about that. If there is a capacitor here, then this capacitor will also come uh, plus that
See that.
C1. Okay.
Sir, while solving the problem, we will consider approximate pole or full pole value.
uh, you can consider approximate pole based on the question that they ask. Okay, if it is asking up to 3 decimal place 4 generally people when they talk about pole location P1, generally this is the expression that they are concerned with. Okay.
Because in last assignment I have around 3 to 4 questions due to point value.
Yeah, I understand that, but So this is what
Yeah,
they
last
generally
time.
mean. Okay, this is what people generally mean when they ask P1 is G naught 1 divided by C times the gain of the second op-amp. Okay, this is what is the meaning. Anyway, P2, what is P2? What is P2 here? Yeah, what is P2?
P2 is given at GM2 into C upon C upon C plus C1
Hmm.
plus GO2 divided by, if the Cl is there, na, so that time they have taken Cl. So it is Cl plus C into Cc1
Correct.
divided by C plus Cc1. C plus C1, sorry.
Right. Divided by Cc1 divided by C plus C1 plus Cl plus something else, right? No need to worry about that. So this is the expression, right? Approximately. Correct. These are the two pole. This thing. Correct. Now, when you do the calculations here, okay, and if you see that the pole locations P1 and P2 are much farther apart, then you can assume a lot of things. You can assume that the profile will be something of this kind. Okay, you can assume that the profile, loop gain profile, will be like this. And after this, P2 hits. This is UGB, this is your P1, and this is your P2. And in this case, what can you say? What did I say? You can say that P1 is much less than omega u loop, okay, and P2 is much greater than omega u loop. You can assume these things to make your calculations easier. Okay, these are the general approximations which people make while solving questions like this, because you have to find omega u, right? In all the questions almost you have to find omega u, and for omega u you have to assume something, otherwise your calculations will become very messy. Okay, so while doing this, if it turns out that P1 and P2 are very farther apart, you can assume that P1 is also much smaller than omega u and P2 is much greater than omega u. Okay, and after that, oh, by the way, in the previous question I forgot to mention this point. Problem, this one, in this problem. So here we followed what method? Here we said that for critical damping zeta should be equal to 1, right? And then we solved the whole equation, and we found out what is the characteristic equation here, which is this one, right? And from here we calculated what is the relation between C1 and C2, right? We could also have done the other thing, that is, we could have simply found out what is the loop gain here, that we did anyway, and from here for critical damping, you remember what is the phase margin approximately? So in the lectures it was mentioned, right? What is the phase margin?
60 degree.
No, 76
62.
degrees is the phase margin. Okay, 60 degrees is the phase margin which is ensured for proper operation. Okay, generally while designing op amps, we ensure that minimum phase margin is 60 degree. Okay, that is what is ensured, but 76 degree is the phase margin which is required for critical damping. Okay, so we could have also solved this question, that basically we wanted to find out the relation between C1 and C2, right? So we could have done that by simply writing the loop gain equation here and trying to find the phase margin here. From the loop gain we can find out what is the phase margin, right? And we could have equated this phase margin to 76 degrees, and from this we could have also found out what is the relation between C1 and C2, and it will come out to be the to be exactly same as the one that we obtained here, right? That C1 is approximately equal to 800 C2. This is the same value we will also get from phase margin calculation. Okay, by the way, okay, so what yeah, Anas, so you have some doubt? Yeah. So you can ask me, unmute yourself and ask me.
Hello.
Yeah,
Yes, sir. Is my voice is audible to you?
yeah. Actually, you're slightly your volume is very low, less. So could you please speak up?
Just a second.
Yeah, yeah.
Now is it clear?
Yeah, now it is clear.
Yes, sir. Sir, actually, I have posted two questions. Can you please give me a reply to that? Sir, actually, I have one doubt that, sir, am I watching the correct course? So, can you please let me know? Sir, link I have given. Because, sir, the videos are very old and the teacher is Professor Nagendra Krishna.
Okay.
So, can you just confirm me because, sir, I am having a little bit of doubt in this.
Okay. So
Yes, sir.
actually the course is being taken. The instructor is Dr. Sankaran Anirudhan. Okay, but
Yes,
he's
sir.
posting the lectures of Professor Nagendra Krishnapura only. For
Yes, sir.
yeah. So up to week 6. Okay, up to week 6 content. It will be
Okay, sir.
delivered. The content will be same as Professor Nagendra Krishnapura's course on analog IC design. Okay, from
Okay,
week
sir.
7 onwards, the content will change. Okay, content
Okay,
will change
okay,
from
sir.
week 7 onwards. It will be different one from week 7. It will be taken by Professor Aniruddhan only. Okay, from week 7
Oh,
onwards.
okay, sir. Okay, sir. Thank you so much, sir.
Thank you.
Thank you so much for clarifying my doubt.
Yeah,
Thank you,
welcome.
sir.
Yeah.
And sir, one more question can I have, sir? Sir, is actually I'm preparing for VLSI interview, so with this course we have.
Yeah, it is extremely beneficial actually. You know
Sir.
that recently this TI had this
Yes, sir.
partition.
Internship I have got. Yes, sir.
Correct. So this
That.
course is extremely helpful. So focus on this course. Okay.
Okay. Okay, sir. For that only I'm preparing.
Yeah, yeah, yeah. Focus on the course, and then you can. It will be really beneficial for you.
Okay, sir.
Okay.
Thank you, sir. Thank you so
Welcome.
much.
Yeah, Srinivasa. I guess you have some doubts. Yeah, Nikhil, you have some doubt.
Yes, sir.
Yes,
Like
sir.
with payload, we will be saying how to find the phase margin, sir. Like I'm getting confused with the
I
last
cannot
question.
hear you. Please, could you speak up, please?
Yeah. Now is audible, sir.
Yeah.
If payload will be changed, how to find the phase margin, sir?
I mean, because of C load, right? This CL, this CL here is
Mm-hmm.
coming in pole P2 location, right? If pole P2 changes
Yeah.
here, if it comes closer to omega U
Mm-hmm.
loop, then basically you have
Mm-hmm.
your phase margin will become poor, right?
Yeah. So here pole will be also changed. All the
Of
poles and
course,
zero will be
P2 will
changed.
change, right? C2 will not,
Okay.
CL
So
does not have much effect on P1, but CL has some effect on P2, right? A very large effect on C2, by the way, on P2, right? So that is why, because of CL, your P2 will change. And let's say that earlier your situation was something like this is P1, okay? And from here you have this omega U loop, and then you have this here you have this P2, okay? This is minus 40 dB per decade, and this is minus 20 dB per decade, okay? And this P2, if capacitor CL increases, what happens to P2? What do you think? P2 will what will happen to P2?
uh, P2 will be shift left side.
Correct. If
Right, sir.
if CL increases, P2 will decrease, isn't it? So if CL increases, then P2 will decrease. Let's say P2 comes to this point, okay? So basically in that case, what will happen? Your second pole location might become like this. So your this thing will start dropping from here itself. So the phase margin, the phase plot will be what? Earlier it would be something of this kind, that from here it will simply go to 90 degrees, okay? And it will remain 90 degrees up till here, and then it will go to 180 degrees, okay? But when P2 comes when P2 is shifted in this direction, then the phase margin, then when the phase plot, will look something like this. So this comes like this here, and it will start dropping here itself. Okay, so you see that in that case your phase margin will become poor, isn't it? Earlier you had this 90-degree phase here, and you had a phase margin of 90 degrees, but now the phase margin is slightly poor. Earlier your phase margin was what? Earlier phase
60
margin was
degrees.
90 degrees
60
like
degrees.
this. No, from in this figure I'm saying.
Yes.
This was like
Okay.
this, right? It is the difference between 180 degree and the place where your omega u becomes omega u loop, right? This is the place. At this place you check what is the phase, and that is why the phase here it looks very close to 90 degree, right? But in the red phase curve it becomes lesser slightly, isn't it?
So we
Sir,
have to
I
find
have
the
So basically
again.
what I'm saying is that when P2 is changing, okay, if P2 is moving this way or this way, your phase margin is changing, isn't it? Your phase plot is changing, and because of that phase margin is changing, so it will have some effect on phase margin. Okay. Yeah, so what question
sir, I
Nikhil?
have one doubt, sir.
Yeah.
Sir, in the magnitude plot,
Uh-huh.
if you show the range of frequencies for the closed loop bandwidth, then it is very easy for us to understand this term, sir.
I didn't understand your question.
Actually, here, sir, you have shown the magnitude plot, right?
This is the
And
magnitude
omega
plot.
u loop you have shown.
This is the loop gain plot.
Yes, loop gain plot.
Huh.
And in this, if you show the range of frequencies for this closed loop bandwidth, the bandwidth if you show, then it is comfortable for us to understand.
I mean, closed loop bandwidth. I'm not talking about closed loop right now. The closed loop, by the
Okay,
way, it will look
this
something like
topic
this.
I understood, sir. What you described that we understood.
Okay,
This
okay.
is another question I am asking.
Okay, okay. So you want me to discuss about closed loop systems also? I mean, closed
Closed
loop
loop
behavior.
bandwidth in this response.
Okay, okay. Okay, so by the way, this is a very simple thing, by the way. Okay, so nothing much to discuss there. You see, if your loop gain response is something like this, uh, okay, if your loop gain is something like this, let's say this is omega u loop, then your closed loop will be something of this kind, magnitude plot. It will be like, no, this is not the same gain. Okay, gain might be lesser for closed loop system. So let's say your gain is like this, and your first pole of the closed loop system will occur here. This will be something like this for the closed loop system. Okay, and this was actually explained in the lectures also very well. So that is why I didn't touch this part, because this is not much to discuss here in this question, actually, in this concept. Actually, the closed loop system is basically behaving like a ideal system till the open loop gain of the loop gain plot, and from after that, after the open loop frequency, it starts going down. Its response starts, basically omega u loop is the pole for closed loop system. So this is this thing. Okay, open loop UGB is same as closed loop 3 dB bandwidth. Okay, and this is strictly true for a first order system, that is system having only one pole. Okay, so if you have any specific doubt, you can ask me. Otherwise, I do not I did not have much to speak about this.
Okay, sir. Okay, sir.
And Nikhil, you have some doubt?
Sir, any textbook for practice this kind of questions, sir? Can you suggest?
Not textbook. I don't know. This textbook, by the way, Razavi's book. Okay, there is also a book by this Sergio Franco. I already said these two names, right? These two books have a lot of questions on negative feedback and things like this.
Thank you, sir.
Yeah. Nikhil, you have some doubt? You have raised your hand.
Like, yeah, like her answer is whatever answer is given us a very tight range. So whatever value we are getting confused which value we have to give or not. So last time I got 2 marks already. Like 2 marks, I not get it. So just
Yeah,
of
so
one
why?
point only.
Yeah, so these things are not in my control. Actually, these things are people who are dealing with this are administrative. Okay, so you can mail these concerns to the authority. Okay, they will look into this. I mean, I cannot do anything about it. This this is computer generated, and we are not checking it. Okay, computer is checking that, and it is
Yeah.
fed by
But
someone else.
sir, but but you are sir telling ki you take approximation for easy to make easy. When I take approximation, then it will happen this thing
Yeah, yeah. So
only.
approximation means I do not know what approximations you make. I mean, when I made the approximations, I also solve the questions, and when I make approximations, they turn out to be correct. So clearly, you are not making the right approximation. So that is why I said, now, while making the approximation, be careful what kind of approximations you are making. I mean, whenever whatever approximation I am making in any of the question that I am solving, these approximations I am justifying right at the end. So the earlier question also I solved, and I made approximation that some capacitor is much larger than the other capacitor. So that approximation is justified at the end. Okay, so that justification, if it is not coming, then you will have issues. I mean, if you're making some approximation, you have to justify it yourself that you are making it the right approximation. And generally, in the questions when you will be solving, they will not be asking you exact answers. Okay, they'll ask you. They do not want you to make. They do not want to make your life uncomfortable by getting you involved with a lot of maths. Okay, they only want to make sure that you understand. For that, they will not ask exact answers. Okay, they will be they will be expecting some approximation here and there. Anyway, if you have very specific concerns, you can mail them. Okay, you can ask them in detail, then it will be solved. Okay, so does that clear it up?
Yes, sir.
Any other person?
Sir, one doubt, sir.
Yeah.
Sir, calculating the ROUT, you have to start circuit, open circuit the VI now, sir, input voltage.
No, you are
So,
not at open circuit. You have to short circuit.
yeah, short circuit, sir. Then it will be only resistance, that is GO1 and GO2 in will be in series, no, sir.
No, you also have to you also have to apply a test voltage, right? You also have to apply a test voltage here, VT, and
Yes,
then you
sir.
have to see what is the current that will flow.
So so this condition capacitor will be open only, right? Sir?
Which capacitor will be open?
Like C Miller effect capacitor. It will
No, no,
behave
no
like open.
capacitor will be open. This is exactly the same like this, right? This is the condition,
Yeah.
and in this you have to simply apply a voltage here. You have to ground it. You apply a voltage here. So why are you saying that this capacitor will be open? There will be all the things
Because
will be
we are
there.
applying. I'm thinking to be a like giving like DC voltage like VTEST. So capacitor will behave like open circuit.
No, nothing will. No, no, no. It will be like this. You solve it by writing KCL KVL equation. Okay, you will find it.
Sir, in that case, which frequency should I take to calculate that
You do not have to
ROUT, sir?
assume any frequency. You have to assume. You have to do everything in terms of S. S is Laplace domain, right?
Yes, sir.
Write everything in terms of S.
SC.
Yeah.
Sir, how to simplify that S to get numbers, sir?
So what was the question, by the way?
ROUT, sir. How to calculate the ROUT?
Let's see. Let's see. Okay, so if they are asking simply like this, then they are probably asking the DC output impedance. Okay, S is equal to 0. You have to assume. I mean DC. You have to find out at DC. Okay.
Yeah.
No, no. If they are asking only a simple number, that means they are asking DC at DC. Okay, that
Yes.
is at S is equal to 0, omega is equal to 0.
Capacitors are open circuit.
Right. Capacitors are open circuit in that case. Yes, true.
So in figure 1, how did we identify which terminal to be connected to the output to have negative feedback? I mean, everyone could say it instantly, so that's why I got confused.
Yeah, so you see, I discussed it, right? I mean, you have to simply check.
Yes, sir. Applying a test voltage and seeing
Yeah,
whether it's the negative.
correct. So that you
But
do,
this
and
time everyone said instantly,
yeah,
so
yeah.
I
So
got confused.
no, that was actually probably because, and they might have understood it very well. And other reason is that here it is already given plus and minus. Okay, so minus
Okay.
terminal has to be connected here. So, but anyway, you can assume. Let's say you connect it like this, and you see that you will see that basically the voltage will not be inverted, but it will in the same phase. Okay,
Okay.
so you will see that this is wrong. So it takes some time. Okay, it takes some time.
Okay,
Don't
sir.
worry about this.
Okay.
So anyway, so I think time is up, right? So let's meet next Sunday. Okay, thank you for joining today's session. So I guess
Thank you so much.
with this you will be able
Thank
to
you,
solve
sir.
the questions. Okay, yeah, welcome.
Thank you, sir.
Any
Thank you.
concern that you have regarding the
Thank you, sir.
question solution, you can mail it to the concerned authority. So this is not actually my jurisdiction, so I cannot do anything about it. Any problem that you have regarding the assignment solution or regarding your marks, that you have to mail to the concerned authorities. Okay, I can
Can
only
you provide?
I can only solve the questions here and make you understand the solution. That's all. I cannot do anything else. Okay, thank you.
Sir, can you provide answer of this question?
What?
The currently solving problem number 3.
What? Yeah, can you come again?
Answer. This problem answer, sir.
No, I cannot do that now. This is exactly the same as what is being asked in your assignment. So I've
The
just put it here. I just put it
the
here to make to just give you some idea. I just,
oh, okay, okay.
that's all. Nothing, not to discuss. I cannot discuss this question. This is exactly the same as the question that is being asked in your assignment. So we'll
Okay, sir.
discuss
Thank you.
this next time if you want to.
Sir,
Yeah.
and the lecture notes for week 1 and week 2 is uploaded, but you can upload the can you upload the week 3, week 4, or week 5 till?
I can upload till week 4. Okay.
Okay,
Yeah. Thank you.
thank you, sir.
Thank you, sir.
Thank you, sir.